Hey, good afternoon, everybody. Welcome to our DEHN Protects webinar series. Today we're talking about the fundamentals of lightning protection. I'd like to introduce myself, Mark Hendricks, and my colleague, Stephen Weber. And just a quick review of what we've got coming on for today, and then next week we're planning to do the Bond That Metal Stuff segment. And today's session, fundamentals of lightning protection. We're really excited about showing our audience the basic premise of lightning protection. I like this photograph that I found, a slightly used lightning rod from Ben Franklin's era. So today's session, what we want to show is how lightning propagates through the atmosphere and how that translates into the concepts of lightning protection. We'd like to talk about how that electric field, how that charge moves, provoking electric field, and that's what causes lightning to step and jump through the atmosphere. We'll talk about final attachment, we'll talk about return strokes. We look at the pillars of lightning protection, and we talk about air terminals, down conductors, earthing. But we also pay a lot of attention to separation distance and bonding, and of course, surge protection devices. So let's get started here. I like these slides. This is a nice simulation, an illustration of what lightning looks like as it propagates. And what we understand about the propagation of lightning is that it's the motion of charge through the air. And as it jumps in several hundreds of meters at a time through the atmosphere, it provokes a huge electric field, and that electric field generates a response to everything around it. So what I like about this illustration is that it shows that lightning isn't just provoking a single attachment point to the earth. It's looking for everything in its sphere of influence, is provoking a small step leader that wants to attach to the rest of the charge. And as lightning propagates, the final step leader initiates the complete return stroke, and now the charge moves through the atmosphere. And what we understand, of course, is that charge is moving only in one direction. It essentially is, although it's a fast pulse, it's a single direction. It's like a big DC event. And what's interesting is the fact that, as I mentioned, it isn't one single attachment point. Everything in the influence of that electric field is trying to reach out to that lightning stroke. So if you're out in the golf course and you feel a little tingle on the back of your neck, that's you. You are essentially provoking a small step leader that, relative to your distance to the charge, will create an electric attachment. So I really like this photo. It's a lightning versus a sycamore tree, and I first saw this in National Geographic magazine quite a few years ago. But what's really nice about this photograph is it's actually showing those small electric tendrils reaching up from other trees in the vicinity and from that antenna mast that's next to the farmhouse. And what you're seeing is the actual little tendrils that tried to reach out to the lightning before it actually attached to the tree. And so this is a really nice photograph that depicts exactly what we were just discussing. So we understand that lightning is charge that moves through the atmosphere. It generates this huge electric field. For those moments while the electric field is getting ready to make its next jump, it's accelerating electrons to near the speed of light, which actually generates X-rays. So there's really great studies from Dr. Uman Martin and his associates that they actually detect these X-ray pulses as the lightning is jumping through the atmosphere. In fact, this exact photograph is on the cover of the Physics of Lightning textbook from Dr. Martin and Anton Raykov, and it's a great illustration. And I have a nice zoomed in illustration of that. You can see some of the step leaders reaching from the lightning off to the upper left, but you can see a nice zoomed in image of that step leader that was trying to attach to the major body of the lightning stroke. So it's just a really nice illustration of that step leader and that final step attachment. That is where the notion of the rolling sphere methods come from. So we know that lightning, that downward leader has a momentary charge. It's building up this huge electric field. The electric field is spherical, propagates in all directions, and it's provoking these upward leaders to try to attach to that charge. And that's what's often called the striking distance. That electric field presenting a sphere is exactly where the rolling sphere method is derived from. And so what we could see is that if you understand that the last final step leader is essentially trying to provoke an attachment in all of three-dimensional space, you can use that as a calculating method to discover where lightning would prefer to attach. And remember, what a lightning rod is doing is it's not making lightning come to it. The lightning's going to strike anyway. What the lightning rod does, what the air terminal does, is it gives the lightning a preferred attachment point, a little bit closer. It becomes the closest point to that downward leader. So that's exactly what Ben Franklin figured out, and that's why he put the lightning rod into public domain, because he figured out that if you give it a preferred attachment point, and if you give it a down conductor and an earthing electrode, you can divert the lightning into the earth safely and prevent fire. And that's what lightning protection is really all about. It's fire protection, fire prevention. So I have a couple of nice slides that talks about what is lightning. What is lightning? It is the motion of charge through the atmosphere. So we have a charge, and I hear this question a lot. Wouldn't it be nice to be able to capture the energy of lightning and use it for useful work? Yes, that would be a really great idea, except that you would need a capacitor that looks like the 10 miles of atmosphere of dielectric withstand that the lightning is punching through in the first place. So if we can develop and discover such enormous capacitors, maybe someday we can capture that energy. But for the time being, our best bet is to just simply divert it safely to Earth and prevent fire. So the parameters of lightning that are widely accepted are the charge. And charge is essentially generates the current that we see. So charge, it's decisive for melting parts. This is essentially what bursts through things like the wall of a tank, or punches through your aluminum roofs. Charge is decisive in melting metal parts at the point where it attaches. The next parameter we talk about that you see in the standards is current. And we saw that current is related to charge through the integral of time. And what's very interesting is that the current that is provoked through that lightning pulse, there's sort of a minimum value that it takes to punch through the atmosphere in the first place. But there's also what's observed as maximum values that are understood to be the range of lightning currents. Lightning comes in many, many flavors, so there's no one formula for what lightning looks like, but there are very useful terms that we have in the standards that help us understand what to test to ensure that our methods and our measures are actually effective. So the peak current is what is the charge flowing through the wires. The other value we talk a lot about is the steepness, the DIDT, the change in current over time, how fast the pulse rises and decays. And this is really important because this is what will generate the voltage across the down conductors across the building. And that will provoke side flash and other causes of flashover around your structure. So as the current flows through the wire, it has a steepness. The wire has some impedance. And we know that the voltage is a function of that steepness times the impedance of the wire. So that will generate what looks like an enormous voltage, kilovolts, almost 1,000,000 volts across the down conductor from top to bottom. That's a very important factor, the steepness of that lightning pulse. And then the final parameter that we talk a lot about is the actual energy. And you can see mathematically that all of these factors are related through mathematical formula. So it's useful to be able to transfer between different factors so that you can charge a generator and determine the current that will be induced. And you can build a lightning test generator that can approximate the effects for the purpose of testing. And again, this is about fire prevention. So we want to make sure that our methods and our connectors all meet the standard so that you can properly protect from fire. So in the IEC 62305 set of standards, it's very useful because we have different lightning protection levels depending on your control of risk. So if you're a nuclear power plant with extreme risk control, or if you're a hospital full of babies and oxygen, or if you're a rocket ship full of hydrazine, you want to be very conservative and you want to guard against the maximum acceptable limits of charge, energy, and peak current. And that's what you see in the standards, is that if you can accept more risk, you're willing to have essentially less lightning current. So that's how this standard in this chart shows. What's important is that you have levels of lightning protection that are less robust than the LPL1, which might be the most controlled of risk. And this is important because if you look at the range of lightning, and what's nice about this slide is it shows that the 99% of lightning is greater than 3 Ka, and 99% of lightning is less than 200 Ka. And these come from the standards and the extensive research conducted by Senelec and Seeger. And there's some brilliant contributions from members such as Anton Raykov that look at we can measure what's happening in lightning, and then you can create a distribution table like this. And what's important is that the LPL1 level is the most controlled of risk. You've handled almost all of the low end of lightning and almost all of the high end of lightning. And that's versus something that looks like LPL3, which is still very robust, but it's ignoring some of the small flavors of lightning, and it's ignoring some of the high current levels of lightning. And what we find in the standards is that LPL level 3 is very close, approximately equal to what's considered the NFPA 780 family of lightning current. So what's nice about this chart is it shows you that if you're willing to accept a little bit more risk, maybe you have something like a warehouse that's full of steel and it's not combustible. Well, then you can accept more risk. But if, as I mentioned, if you have a hospital, then you're not willing to accept risk. So you want to guard against more effects of lightning. And what's very interesting about this is it's the low end is what actually sneaks into all the nooks and crannies. So if you're worried about protecting all of the structure around your hospital, then you have to look at the low end of lightning current. So what we know about lightning is that if it's a small charge that is inducing a small amount of current, say in this low range of 3,000 amps, it will generate a rolling sphere that is smaller, and it will essentially sneak into all the nooks and crannies. So a smaller sphere is considered worse because it can attach to other things that you might have thought you had protected against. And what I like about this illustration above here is that it shows that if you place your air terminals, you can essentially build that rolling sphere model and show that you've suitably applied lightning air terminals where they will be effective to capture that stroke. If you have a larger rolling sphere, essentially you need fewer lightning rods. And that's really how it equates. If you want to control your risk to a more robust level, you need more lightning rods, and you apply them based on the rolling sphere methods, and you can calculate where to place the rods so that your structures are properly protected. Of course, there's other protection methods. You can apply a mesh, you can apply a protection angle. This is often seen around the electrical substations here in Florida, for instance. If you have a substation, you can predict the angle that it will, that the protection below that air terminal. And so this is a nice slide because DEHN, we do a lot with rolling sphere calculations, but there are other methods that are very effective, including a mesh, where you simply lay a mesh of conductors and air terminals over your structure, and you can get a very effective lightning protection solution for your structure. And again, it's all about controlling risk. If you're more concerned, then you use smaller meshes and a smaller rolling sphere radius. And so this comes right out of the table. And again, I'd just like to remind you that the LPL level 3 is essentially equivalent to the NFPA 780. So NFPA 780 also promotes the use of the rolling sphere methods for a 150-foot radius sphere, which is essentially a 45-meter equivalent rolling sphere. So again, I like to draw that equivalent. You'll see a lot of things that are more similar between the standards than different. The major difference, of course, being that the IEC methods recognize more flavors of lightning to give the designer more leeway in providing more protection. So the pillars of lightning, the fundamental pillars of lightning basically dictate that you apply an air terminal. This is the air terminal on the top of the structure, the down conductor system, the downcomers that bring the lightning currents to Earth, and then the Earth termination system. This was essentially what Ben Franklin introduced in 1753. But keep in mind, there's also separation distance that you have to be aware of between your lightning down conductor system and other metal bodies, because what lightning wants to do is remember, we talked about that current and the voltage that it will build up in that down conductor. Well, if you build up enough voltage, it will want to flash to other structures around your building, other metal pieces of equipment. And then the last piece of the fundamental pillar of lightning protection is equipotential bonding. So what we say is bond it together. If there's metal, you should bond it so that it doesn't accidentally flash to it. And what's important about that is you'll see in photographs such as this, lightning will flash over into your electrical systems. So you can't necessarily bond your electrical power conductors, so you have to separate them. So that's really what you want to pay attention to. And so whenever we're discussing an aspect of lightning protection, say the placement of air terminals, you always need to pay attention to all of the factors. You need to look at your down conductor and your earthing, but you have to always pay attention to the separation distance and to the bonding of metal structures. And this shows up in both IEC and NFPA standards for bonding distance and separation distance, which essentially are very similar or the same thing. And this is a nice illustration of what that looks like. When you're applying your air terminals, you want to put them in logical, effective places so that you can capture the lightning stroke, but also keep it away from other parts of your electrical system. So in this illustration, we see something that might be solar panels or an important electrical system on the roof. Maybe it's antennas, like you see here, there's a small antenna, or maybe it's the chiller on the top of your roof, or something that might be, think of a data center, and that's covered with chillers to keep the important computer equipment protected from heat. So something like this is a really nice illustration that shows you attach the lightning protection terminals to the metal flashing of the roof, but you separate the air terminals from the very sensitive victims that you're actually trying to protect on your roof structure. And here's a really nice illustration photograph that shows exactly that concept. You have a down conductor that's passing right next to electrical lighting and electrical, maybe security sensors, and what you will have is something that looked like that photograph from the other slide, where lightning will be, it'll attach to your air terminal, which is what you want. It'll come down the down conductor system, which is what you want, but you got to pay attention to your separation distance. So what's important is that it's a nice photograph of paying attention to all of the parameters at the same time. You have to always pay attention to separation and the location of your down conductor system. The next piece, the logical piece in your lightning protection system, is going to be your earth termination system. In IEC methods and in NFPA methods, they describe what's called the type A, which is essentially it'll look like either an electrode that's radiating away from the structure, and we see the term at least 5 meters, and this we'll see in the next slide. We'll talk about that some more. But also, it can take the place of a vertical earthing rod, and this is something that you might even see at your own residential dwelling. Right next to your incoming AC power is your NEC Article 250 earthing rod, and that is for electrical safety, but also you see all of that metal around it bonded together. Another very effective type of electrode, the type B, which looks like a ring electrode around the structure. And this is very common in what might be power plants where you have multiple buildings and you'll see a grid of buried rings that are all interconnected. And this is also similar to what's considered the foundation earth electrode. So this, you often hear the term the Ufer ground, which is essentially using the concrete and the embedded electrical, the embedded rebar in the concrete as an electrode, and they all work correctly if in fact bonded and created. And we'll see a few images of this as well. This is an interesting slide because it shows you that the earth electrode needs to correlate with the class of lightning protection you intend to apply on your structure. So if you're working within what looks like the class 3 or the class 4 lightning protection methods, you can develop the diameter of your rolling sphere, but you can also calculate how deep and how much contact that your earth electrode has to have with the soil. So in this chart, you see that it's essentially a 5-meter earth electrode contact. So when you're designing your earthing system and you first look at the soil resistivity. So of course, if you're in a dry, rocky soil, it might have a very high soil resistivity. And if you're attempting to implement a class 1 lightning protection system in 1,000 ohm meter soil, you see that high resistivity means you have to have more electrode in contact with the soil. So you'll have a deeper electrode, you'll have longer radial electrodes. And this is nice because it shows you that if you really are working on a more stringent class 1 or a class 2 system, you'll need more electrode in contact with the soil. As opposed to class 3 and 4, it's essentially understood that 5 meters of electrode contact is suitable for the standard. What also happens is that you see customers have their own relative requirements for electrode placement and electrode impedance with the soil. So for instance, we have power utility companies that want a 1 ohm electrode contact with the soil. And you have the National Electric Code that indicates that you need not more than 25 ohms for a residential dwelling. So you see this in various standards, but what's important is that if you know the class of LPL system that you want to install, you can further calculate how much earth electrode it will take to effectively dissipate that charge into the soil. And of course, we saw that in the standard. If you're trying to dissipate 200,000 amps of lightning current, you're going to need more electrode, and that's essentially what you see in a chart like this. Separation distance. Now we saw that side flash photograph, and that is essentially what's happening. The lightning is attached to the air terminal, which is correct, and the current is flowing down the down conductor. But as it's flowing, it's building up voltage because of that steepness. Remember, we talked about the steepness of the current. Well, a steep pulse will induce a lot of voltage. Well, that will cause the side flash. And that's what you see in that photograph from the other slide. It's trying to find other paths. And so you need to maintain suitable separation from the down conductor system. And that's what's nice about this particular slide, is it's talking about separation distance. In the NFPA systems, NFPA 780 also gives you a calculation for what's called bonding distance. And that distance is essentially the same thing. It turns out that separation distance for an IEC system at LPL3 is essentially the same calculation. It's actually mathematically within a few percent different from the calculation for NFPA bonding distance. It's essentially the same thing. If you're running your down conductor next to a piece of metal, you have to bond to it. And this is what you see in something like a photograph like this, where the designer put a lightning air terminal right next to a metal control box, but they did not maintain suitable separation from that metal box. And then you see in the background, you see an air, maybe some sort of heating vent come up from the roof, and here it's bonded. So either you separate from it or you bond to it. And that's what the standard basically dictates. When you look at your pillars of lightning protection, you either separate or you bond to it. And that's why I mentioned you ignore this at your own peril. So in this case, if lightning were to attach to this air terminal, it will try to flash to this electrical control box that might be up there for a very important reason. For instance, controlling radios or controlling your air conditioning equipment for a structure. And so a photograph like this actually shows you a lot of the same aspects we've been talking about. You've got air terminal placement, you've got your conductor system. It might be a mesh. It has various air terminals attached to it, but you have to pay attention to all the aspects of lightning protection and not ignore any of them. Otherwise, you'll introduce side flash, for instance. And then we talk about lightning equipotential bonding. This is the other side of the coin, either separate it or bond to it. And what's nice about an image like this is you can see that all of the metal within this structure needs to be bonded together. And this is what you see within the buried rebar of concrete. We have a clamping and a connection system into that rebar system to make sure that it's not loosely bonded. And that's a term that you see a lot, is a casual connection. Very often you'll see in rebar, of course, it's wires strapped together, or sometimes it's CAD welded together. But what you see is buried rebar in that concrete. And if you have something like this pillar that is casually bonded together, if there's lightning currents flowing through that rebar, it will arc and spark within the buried concrete, which will spall the concrete and cause failure over time. And along with corrosion and water ingress, the simple fact that lightning might be hitting your concrete support members is going to induce premature failure if it's not bonded together, equipotentially bonded throughout that mesh of rebar. And this is really important because if it's loosely connected, it could be arky and sparky on the inside. And then we talk about electrical bonding. Now, of course, you can't take your incoming AC power and bond it to your earthing system. That's what electrical power is doing. You're not bonding it. So that's what the surge protection device serves. The surge protection device, the SPD, serves as that momentary bond to control that side flash voltage so that it doesn't puncture into your conductors or blow out your data control system or your sensitive radio on the top of your antenna system or your security camera systems that are mounted around the side of the structure. Of course, in our world today, we have Wi-Fi systems everywhere. We have security camera systems. In the UK, there's more cameras than people. And all of those electrical apparatus have to be protected. And so you can't bond it, so you apply surge protection. And that's what an image like this is showing is you look at all of your apparatus and you apply appropriate surge protection methods. And in this instance, you can see a couple of nice images of the surge protection device at the electrical panel, which is right at that main distribution system, or at your low voltage control systems that have to be protected in the case of lightning currents being induced around it. And remember, lightning isn't always being conducted into the electrical power. What might happen on a building like this is lightning hits the air terminal, is safely conducted into the soil, but as that lightning charge is attempting to dissipate, it's building what's called a ground potential rise. And so the lightning currents aren't necessarily coming from the power. The lightning currents are coming backwards from the earth, and it's inducing it into your electrical control panel, essentially upside down. It's coming from that ground potential rise, and those voltages are trying to break into the dielectric of the electrical wires, and that's what your surge protector does, is it prevents an overvoltage from breaking down the dielectric of sensitive computers, of your sensitive control systems and cameras. What's nice about this photograph is this illustration, it shows exactly the concepts that we've been talking about. You've got a lightning air terminal up above the victim equipment. In this case, it's a radar type of a shelter, for instance. And what you've got is the calculated fall of protection angle. This is one of the alternate methods. It doesn't always have to be a rolling sphere calculation. In this case, a single air terminal, you can calculate the fall of protection angle. Essentially, the things that are below this angle are considered protected. And this is what you see in the standards called the zone of protection. And you can build a more and more robust protected zone. But what's very nice about this illustration is that you see the down conductor, and that's you have the air terminal, you have this red lightning mast, and then you have the down conductor. And in this application, we've used some of our DEHN products that provide prevention of side flash. The conductor prevents side flash from entering the structure. And what you get is essentially the ability to build two grounding systems that are separated with enough distance so that if you get a lightning strike, you can safely divert the current away from the structure into the earthing system. So here you have all of the aspects illustrated in one nice shot. You have the air terminal, down conductor, and an isolated type A earthing electrode. And then at the structure itself, the blue, it might look like a blue shelter, maybe a metal ISO container that has its own earthing rod. And with suitable distance through the soil, you can prevent that ground potential rise from polluting your ground system of that shelter. And so what was important for this customer is that they protect this structure from lightning and from the ground potential rise that would incur if the soil induces that ground potential rise into the structure itself. So in one nice illustration, you have all those aspects we've discussed, including separation distance. And this is a really nice photo this is an image captured from Google of Launch Complex 40 out at Cape Canaveral. And here you see exactly what the lightning protection is for. You have these very tall towers built in a perimeter around the launch platform. So you have this high value asset that's full of explosive hydrazine. And what NASA has done here, they've used all the principles we just talked about, and they've built a protection zone around that launch complex. And in one photograph, again, you can see all the aspects. You have the air terminal, a down conductor system, an earthing system that's separate from the launch vehicle. You've got separation distance, and then around the launch vehicle, you'll have equipotential bonding. So in one illustration, you can see all of the aspects of lightning protection. And these engineers at NASA have a pretty good understanding of the principles of lightning. And so in one photograph, you can see exactly what we're trying to create is a protected system with all the aspects of lightning, the fundamental pillars of lightning protection, all being correctly employed to produce a protected zone around and below that set of towers. So I've got a quick summary of standards. This is a snapshot. This is a partial list of standards. We've discussed a lot of the aspects of IEC 62305 today, which are I would say, very well harmonized with NFPA 780, but that also is very similar to what you see in British standards. And it's also very similar to what you see in the MIL standards that our customers often employ. So the MIL standards 1257 and 464, they're very similar. They have very similar definitions of the lightning stroke itself. There's numerous Seeger publications and from Senelec where I mentioned experts such as Raykov and Martin participate in numerous publications from international lightning meteorological and lightning discharge conferences. And a lot of the aspects that we're talking about are very detailed publications that help describe exactly what we talked about with charge, dissipation, charge, the step leader type aspects, and it helps acknowledge the types of rolling sphere and different fall of angle protection methods that are out there. And of course, then you'll have local variations in jurisdictions. For instance, Florida has particular lightning protection code for schools and hospitals that aren't quite as important in some of the northern climates with a less severe lightning weather phenomena. And so just a quick review, what we talked about today was that step leader attachment. We explained the electric field and how it provokes the step leaders. And that is a great introduction into the rolling sphere concepts, that final step leader looks like a spherical electric field effect. We talked about the final attachment. We also talked about those other step leaders that didn't necessarily cause the final attachment, but they also had a little bit of lightning energy in them, which still would have blown out things like that TV antenna we saw in one of our earlier photographs. And then we talked about the pillars of lightning protection, your air terminal, down conductor, earthing system. We pay attention to separation distance, to bonding it, and then of course for surge protection devices, which essentially forms a separation but a bonding at the same time that allows that momentary bonding and control of the voltages. So I'd like to open up if we have any questions that have come in for our call today.
Hi, Mark. Yes, we did receive a few questions. I will just go to our first question that we received. How can you implement the rolling sphere in an actual application? You had a follow-up question here as well. Looking at equipment on a roof, how can I ensure that the equipment is protected by a lighting protection system without having a computer or anything while I'm conducting a site review of my buildings?
Well, there's still some calculations that you would need to employ to guarantee that the air terminals are above and away from your victim equipment. Stephen, I might let you discuss that because you're very adept at sort of the intuitive placement of lightning rods as well.
No, you're 100% correct, Mark. I just want to say that you can take into consideration the distance that the lighting protection components are away from each other, and remember that every sphere has a penetration arc, so you can calculate what that depth of penetration of the rolling sphere would be between the air termination rods, and if that penetration is more than the height of your equipment on the roof, you know that the equipment is not within the zone of protection. So you can look at things like that, and that will tell you if the protection zone provided is sufficient. But another way is to calculate that protective angle, is take the height of that air termination rod and go to the standards, and find what would be that calculated protection angle. And it's also in our red book that you can find on our lighting protection guide that you can find on our website, and that angle will tell you if your equipment is within that zone of protection. And
yeah, you mentioned that the rolling sphere will essentially sag between the two air terminals, and it looks like an arc falling. You know, you're holding up a circus tent. And
yes,
as the fabric sags, you don't want that sag to touch your victim equipment.
Yes, and I see this question is almost in the same train of thought, is looking at an installed lighting protection system. Is there a way that I can somehow determine the lighting protection level that it was designed according to? Mark, I'd just like to make the comment with this one is there's a couple of things that are factors that are dependent on the class of lighting protection level according to the standards, and one of them are, well, the first thing is basically the rolling sphere. So if you employ this method where you can calculate the sag that the rolling sphere would be, would also guide you towards radius would be of the rolling sphere used. So from there you can then calculate what lighting or see what lighting protection level was used. But another thing is there's also typical preferred distances between the down conductors that the standard gives. So you can also look at the lighting protection level or lighting protection system and see the amount of down conductors, and that will also give you an idea of what lighting protection level it was designed according to. And then, like Mark said, the separation distance, that's also something that can guide you towards what lighting protection level the design was done according to. Mark,
Yeah,
do you have anything to add?
sure. The spacing of the air terminals, the closer together, if they're particularly close together, you might infer that it was a severe standard that they were trying to meet. If the mesh, it maybe looks like a mesh. If the mesh is very tight, that's a more severe adherence to the standard. So yeah, there might be ways to back into what the designer's thought process was. In NFPA, there's basically two flavors. You have a 75-foot building. If it's taller than 75 foot, you put in taller tips, heavier gauge wires, heavier gauge air terminals. If it's less than the height of 75 feet, then you can use what's considered class 1 lighter gauge materials. So in the NFPA methods, it's a lot more easier. There's really only one set of standards, and if it's tall, you do that. So
Yeah, I'm glad you mentioned the NFPA. The question here is, can an NFPA or an ESE system provide a protection zone when and can it be determined with the rolling sphere? Thus, can I assess an NFPA system with the methods in IEC?
yeah, essentially the NFPA methods are identical as an LPL3 system. So if you know the system was designed for an NFPA class 1 system below 75 feet tall, you can infer that it's very similar to an LPL3 protection design.
Yeah, so you can basically take the rolling sphere and roll it over the terminals as they are placed for an NFPA system, and the zone of protection can be calculated according to that. And another point I want to mention here is that if you do have ESE air termination rods or masts in your facility, the IEC, you can employ the IEC methods to calculate what would be the IEC zone of protection that you can receive from these ESE devices. It will be significantly less than what the ESE manufacturers would say it is, but at least it's then based on an IEC method. Anything you want to add about ESE technology and IEC methods, Mark?
Well, yeah, there's some really great publications that have been research done by Dr. Uman Martin and Dr. Anton Raykov, and basically they've determined that an ESE device is essentially the same, it offers the same performance as an air terminal. It doesn't provide a greater radius of protection. It doesn't do anything more than act essentially like a lightning rod.
Yes,
And that's findings from the industry experts.
I just also want to mention we have received customers that have requested from us to assess an ESE system that they have on their PV plant or on their facility according to IEC methods, and in that way we could show to them what is the actual protection that these ESE masts provide according to IEC, and then we kind of gave them recommendations that they can then employ to expand this zone of protection. So it is possible. And it is something that can be done. Marco, I have a question here. It's relevant to the rolling sphere calculation and the LPL levels. Can I calculate a smaller or a bigger rolling sphere with the provided formula that you have in your presentation to provide a custom lighting protection level, say something between LPL 2 and 3? So, or do I need to stick to the levels defined in the standard? There's a question posed by Asman.
I haven't heard it applied that way, but one could essentially come up with what might be a LPL level 2.5 if you know that the low end of the current is what dictates the diameter of that rolling sphere, the radius of the rolling sphere. So if you wanted to come up with a intermediate level, I'm sure you could do it. The problem is that somebody that comes back and inspects it will only be able to look at a 2 or a 3. They don't really have a standard, doesn't necessarily give guidance to the middle of the in-between level.
I think this is a very interesting question. I think this comes where people need to, they're trying to create a light protection system that can address lightning currents smaller than 3 kA. So something like a 10-meter radius rolling sphere, or even if they've done their research and they see that an area normally gets lightning strikes more than 16 kA, they try and develop a rolling sphere that's bigger than the general 60 meters rolling sphere radius rolling sphere for LPL4. But it's like you say, Mark, and I agree that the standard just doesn't give guidelines, and equipment ratings have not really been done according to those things. So but yeah,
yeah, that's a really good point, Stephen, is that the IEC standard indicates not only the low end of the lightning content. If it's a baby lightning stroke, for instance, it might have a small rolling sphere, but it also dictates the high end of the amount of current that might be present in the lightning bolt. And so all of the down conductor materials and the connectors are all tested and rated and have been surge lightning tested to validate that it meets that LPL level. So you're designing a system for the smallest lightning stroke, and you're placing the air terminal spacing to capture a small stroke, but you're also applying materials that can withstand the high end of the stroke. So when you go into the intermediate sort of, can I do a 2.5? Well, you haven't really, you need to design the material for to also withstand what the IEC standard will dictate. So there may be methods to become, let's say, more risk control, but you still need to look at the standard for what the high end might also be. Because remember, it's a high and a low end of the strike.
Yes, I think we have time for one more question. The rest of the questions I just want to mention will be addressed per email. When the down conductor system is connected to the same earthing as my main earth bus bar in my panel, am I not deliberately injecting lightning current into my panel? And a follow-up question from the same person is, can I ground equipment then with the down conductor system?
Ooh, yeah, good question. Because what's intended is that the master ground bar at a facility is connected to the earth electrode in the ground. So you don't want to divert your lightning down conductor onto your master bar and then shunt it into earth. It needs to go to earth first. And the parallel to that, the sort of the corollary to that comment is, you don't want to earth anything to that down conductor until it's buried. So once it's in the ground, the master ground bar pigtail comes back up out of the earth onto your master ground bar. So the intent is to get the charge into the earth first and let it control that and dissipate that charge. And that's why we talk about that ground potential rise. You can't get rid of the charge without it talking a little bit. And so again, one of our customers had asked for us to design a system that had completely separate electrodes that were spaced far enough apart to avoid ground potential rise, because that's what's polluting your electrical system. It's coming back up into your master ground bar, and that's why everything needs to be bonded. So you can't get rid of the charge. If everything's equipotential bonded, it's like a bird on a wire. You won't necessarily feel that electric ground potential rise because everything's together, but it needs to go to the earth first.
Yes, and Mark, I just want to say you've addressed some of the aspects that we will be addressing in our webinar next week, Thursday. So guys, if you want to get a bit more information about equipotential bonding and surge protection and those type of things, and like Mark said, current dispersion into the earth and bonding your systems for that equipotential rise that we're going to see, please join us next week, Thursday, same time, same place. I will be sending you guys invitations per email. And yes, Mark, thank you for the webinar. Thank you everybody for joining.
Thanks everybody for joining. Have a great day. Be safe out there.
Bye-bye.
Bye-bye.